Hello again. Welcome to our third section of Chapter 3, where we are talking about optimization with linear programming. Sounds special, doesn't it? It is. So what we're going to basically be doing today is using systems of linear inequalities to solve real-world problems. And when we talk about optimization, we're talking about maximizing or minimizing things like profit or the amount of something that we can produce. And that is one area where linear inequalities are really practical. And we're going to use the vertices of a region like we did in the last section to find the maximum and minimum values. So we have a lot of new vocabulary in this section. I would suggest you pause for a second to fill in what is written, and then we'll talk about it. So linear programming, like we just talked about, is the process of finding maximum or minimum values of a function for a region that we define by a system of inequalities. The constraints are those inequalities. So for example, we say we can only make 10 pizzas per hour, and we have to spend less than $200, and we need to have more than 3 people working, things like that. All of those things are the constraints or the conditions that have to be met. The feasible region is like the solution area of a system of inequalities, like we saw yesterday. It's the solution area. And so when we graph, we look for the shaded area, and that's called our feasible region, meaning the points in that shaded region are the feasible or the realistic points that could meet our constraints. We're usually looking for a bounded region in this kind of problem, which is when I graph my inequalities, I get a triangle or a rectangle or some kind of polygon. It's closed. An unbounded region would be like it's bounded on one side, maybe like this, but then my shaded area, if this was my shaded area, would go on forever. We call that open or unbounded. And when I'm optimizing something, I'm seeking the optimal or the best price or amount that's desired to minimize cost or maximize profit. So here's our feasible region. This makes it a little bit more visual for you. Here's an example of a bounded feasible region. So here would be my solution area. This is an example of an unbounded feasible region. And the vertices, remember, are the places where at the corners of our feasible region, those inequalities that I graphed represent the constraints. So let's look at an example of a bounded region. So when we take a look at this graph, we are given a set of 3 inequalities. Those are my constraints. Okay, so notice here they graphed them. Here's the vertical line x equals 5, so x less than or equal to 5 is shaded to the left of that. Y is less than or equal to 4, that's this horizontal line here, and we shade below that because it's less than or equal to. And then this inequality is the same as y is greater than or equal to negative x plus 2. That's this constraint here, and it's shaded above it because it's greater than or equal to. So this blue region represents our feasible region. Now notice I have 3 constraints, but they also gave me a function. So they're saying this function of x and y equals 3x minus 2y. So what I'm going to do is I'm going to take each of my vertices. We have 3 vertices for this region, negative 2, 4, 5, 4, and 5, negative 3. And the maximum or minimum value of a region always happens at the vertices. And so I'm going to plug my vertices into this function and figure out which value will give me the greatest or least value. So we're going to use a table. Here, these x and y coordinates represent my vertices. This is the function they gave me, f of x, y. And so, for example, if x is negative 2, I plug negative 2 in for x. Here I'd plug 4 in for y. So 3 times negative 2 is negative 6. Minus 8 gives me negative 14. I plug in 5, negative 3, and 5, 4, and I do the same thing, and I get 3 different values, negative 14, 21, and 7. The smallest of those values has to be the minimum value of the region, and the largest has to be the maximum value. So the maximum value here is 21, and that happens at the vertex 5, negative 3. The minimum value is negative 14, and that happens at the vertex negative 2, 4. Right, so I want you guys to do that same thing for the situation. Here we have 3 inequalities. Here you have the function, So graph the inequalities first, find their vertices, and then find the maximum or minimum values. All right, hopefully you answered B. Your maximum happens at the vertex 4, 2, which gives you 10, and the minimum happens at the vertex 1, 5, which gives you negative 11. All right, now we're going to look at an example of an unbounded region. So we're going to do the same thing we did in the last example, and we're going to graph our system of inequalities. So each of these, you can see here they have the arrows to the boundary lines that they graphed. So this was the boundary line x plus y equals negative 2. Since the inequality is actually greater than or equal to, they shaded above it to the side, and you would see that by plugging in a point. X minus 2y equals 4 is here, and since even though it's less than or equal to, if I were to solve this for y, when I solve this for y, I get y is greater than or equal to x over 2 minus 2, because I end up dividing by this negative 2 that's by the y, which switches the inequality. And then x plus y is greater than or equal to negative 2. That is graphed right here. Oh, I already talked about that one. I forgot to talk about the first one. Negative x plus 2y equals 2, and then when I shade it, I would shade below. So this blue region is my shaded region, and notice it's unbounded. There's no boundary, there's no end on this side. So the two vertices that I get are negative 2, 0, and 0, negative 2. So when I plug those in, I get two values, negative 4 and negative 6. Again, I'm plugging them into this function, f of x, y. And so my minimum value here is going to be negative 6. That's the smallest value that I would get. This is bigger than negative 6, but because my region is unbounded, I can't say that that's the maximum value. For example, if we look at the point 2, 1, you can see that when I plug 2 in for x and 1 in for y, I would get 7. Or if I look at the point 3, 1, I would get 9. So we can see that we can very easily find points that will give us a greater value than negative 4. So since this is unbounded, it looks like there's no maximum value. So try this one. Okay, in this case, we end up with a maximum value of 6, and there's no minimum because of the way that this region is unbounded. Okay, if you have questions about that one, you can ask me in class, but you should be able to see that if you plugged in other points, you would be able to keep finding numbers or values that would be smaller and smaller, and you can see that from that there is no minimum value. All right, now we're getting to the part that everyone always loves the most, the part about word problems, real-world application of math. So there are 7 steps that your book talks you through, which sounds long, but really isn't too bad. Step 1, define our variables, always. Step 2, we write our system, and then we graph it. Then we find the coordinates of the vertices, get our function that we need to maximize, substitute the coordinates, and then answer the problem by finding the maximum or minimum. The hardest part of this whole process is step 2. Usually the hardest part is getting the correct system of inequalities. The rest of it, graphing, getting the coordinates, plugging them in, finding the maximum or minimum, that's all the stuff that we just did in the first 2 examples. It's the word problem part, the writing the inequalities, the system of inequalities, that can be tricky. So let's take a look at this. Let's look at our pertinent information here. All right, let's look at what we have. Here I've underlined the things that it looks like we're going to use to write our system of inequalities and our function. So we know that that the company needs 1 hour for a mowing job and 3 hours for a pruning job. And each crew cannot do more than 2 pruning jobs per day, and they can have a maximum of 9 hours per day. Okay, all of that is going to have to do with my inequalities. Then down here, we have some money information. Mowing a lawn costs $40 and pruning shrubbery costs $120. We're going to use those 2 pieces of information to write our function or our equation later. So what we want to do is maximize the income. So if you were this business owner, you would be wondering, what would be the best combo of lawns and shrubs that I could do to make the most amount of money in a day, knowing that I can only do 2 shrub pruning jobs per day. So step 1 is to define our variables. So we're going to let M equal the number of mowing jobs that we have, and P is going to be the number of pruning jobs. And then we're going to write our system. This is a key thing to think about in any of these problems. They don't state it specifically, but you need to use your logic and know that you're not going to mow a negative number of lawns or prune a negative number of bushes. So both of these inequalities have to be true. The number of lawns has to be greater than or equal to 0, and the number of pruning jobs has to be greater than or equal to 0. Mowing jobs take 1 hour, pruning jobs take 3 hours, and I can only have 9 hours or less to do the jobs. So what we can write from that is that 1 hour per mowing job plus 3 hours per pruning job has to be less than or equal to 9. So remember, m is the number of mowing jobs. This coefficient here is the number of hours, so that I end up with hours. And we also saw that there could be no more than 2 pruning jobs per day. So the number of pruning jobs has to be less than or equal to 2. Okay, so that is our system of inequalities. We have actually 4 inequalities here. We have these 2 inequalities. We have m plus 3p is less than or equal to 9, and p is less than or equal to 2. So hopefully you're writing those down on your note guide or in your notes so that you'll have them to look at when we look at the next slide. So here, notice we're in the first quadrant, right? So here we labeled m as my x-axis and p is my y-axis. You could do it the other way as long as you're consistent. But here we're keeping everything in the first quadrant. So this line right here, p equals 2, that represents the p is less than or equal to 2 constraint. And it has to be less than or equal to that, so we shade below that line. Here's m plus 3p equals 9. Remember that that inequality is actually m plus 3p is less than or equal to 9. So when you solve that and you would shade this direction. And then it has to be greater than 0 in both directions, so that leaves me with this quadrilateral region, and I have 4 vertices, 3, 2, 0, 2, 0, 0, and 9, 0. So I'm going to maximize my income by plugging those 4 vertices into the function. But what is the function? The function that describes our income. Remember, what we're maximizing is income, meaning how much money are we making? We said that we made $40 per mowing job, so 40 times the number of mowing jobs plus $120 times the number of pruning jobs. So that's our function of mowing and pruning jobs. That's our income function, and we want to find the maximum value. So that's when we use our table. Here you'll see my 4 vertices that we got from our graph. Each of them are plugged into my income function that will help me to maximize how much I can make. So if you look at these, obviously 0, 0 is going to make me nothing. If I do no pruning jobs and no mowing jobs, I make no money. There are actually 2 points that give me a maximum here. Both 3, 2 and 9, 0. So let me stay here for a second and think about what this means. So if I mow 3 lawns and prune 2 sets of shrubbery, I would make $360. Or if I mow 9 lawns and do no shrubbery, I would make $360. So there are 2 ways for me to make a maximum income. Either mow 3 and prune 2 or mow 9. And my maximum income that I could make would be $360. Sorry, we should put that here. $360 would be the maximum income that we could make. Okay, this is your last one. I want you guys to try this one. So you'll probably want to pause here for a second and read it, do all of your setup, and then move on to answer the question. All right, hopefully you answered B. All right, so 4 mulching and 0 raking would give you the maximum income. Just to go back here for a second, your system of inequalities should have looked like this. So you have 4 inequalities. M and R both have to be greater than or equal to 0. The maximum number of raking jobs in one day is 2, so R has to be less than or equal to 2. And if I spend 2 hours per mulching job and 4 hours per raking job, sorry, that should be an R, not an H, I would have to have less than or equal to 8 hours total. So that would be the system that you need to graph and find the vertices to get B as your answer. And to get our function, real quick, I forgot to write that. The function you should have used to plug into to maximize the income is 30M plus 50R. $30 per mulching job, $50 per raking job.